Hello guys, welcome to my YouTube channel. My name is Michael and I will be taking you through a continuation of my video on inter-AS MPLS VPN option B. Today I will take you through the last method of option B, which is using the multi-hop approach in order to establish or to design and deploy the option B scenario. The agenda I will be working with today is as follows. I will show you here the recap on the previous lesson, which is option B using redistribute connected method, and also a recap on the route target rewrite feature on inter-AS MPLS VPN network. After which I will delve into the case study for today, which is the topic option B using Multihop Method. After then, I will show you the configuration section where I am going to be displaying how things are to be configured in such a network when you are deploying option B using multi-hop method. Here's a caution. Please note that the designs, the topologies, and IP addresses, including the configurations, are used only for illustration of this presentation, and they do not represent any real-life entity or infrastructure. They are only imaginary and fictitious. Now to the recap. In my previous lesson on option B using distribute connected method, I showed you how things work in comparison to the first option or the first method in option B, which is the next up self. If you want to get the full details on this one, please look at the description for the link that gives detail about the redistribute connected method of option B. Now, on the redistribute connected method, you will recall from the previous lesson that the ASBRs do not rewrite the next up address of prefixes that are learned from the remote AS, which in other words means R1 and R4 being the ASBR of service provider 1 will not rewrite the next up address of the prefixes that are learned from service provider 3 from R10 and R11 respectively with their own IP addresses. They just take those IPs and they redistribute the connected inter-AS links into the IGP of the local AS, which in this case R1 will learn the remote routes from this SP and redistribute connected inter-AS link, which is this link, into its local IGP. And that's exactly what is explained here. And the same thing is done also on R4, likewise R9 and R10. So this is actually the uniqueness of option B using the redistribute connected method as explained in detail on the previous video. And here we also have to consider how these remotely learned prefixes are going to be injected into the local VRF of this PE, in this case R3. Remember, these are two different service provider companies, and so they may not be using the exact VRF parameters at both ends, which is why you have to consider the importation of these prefixes that are coming from the remote end into the local VRF of this local SP. Alternatively, you can also look at the route target rewrite option, which is also a feature that you can consider when you do not want to use the import statement of the VRF configuration on PEs. You can actually consider this option of rewriting the AS route target rewrite option. And so in that case, it means you rewrite whatever you're getting from the remote ends into the locally recognized VRF information, which is the route target, and that will solve the problem on the PEs as well. The main topic for today's lesson is actually the option B, using the multi-hop method. Sometimes you will come across this as using the EBGP multi-hop method. So it all depends on the writer or the author of whatever documentation you're using. But they are all saying the same thing, where you have to specify the EBGP multi-hop values, because in this case, the MP-BGP session is actually formed or established between the loopback addresses, which is not directly connected as they see each other. So if you run a trace route from R1 to R10, for instance, you have to see two hops, which shows that the next hop, which is the peer IP, is more than one hop, at least more than one hop away. And they could be somewhere else. It all depends on the design of the networks anyway. So why do you need multi-hop method when deploying option B? Unlike the previous methods, which includes the next hop self approach or the distribute connected approach. The simple reason is that sometimes, depending on the business requirement of your network, you may be tasked to consider a form of high availability through a particular path between two ASBRs. In this case, for instance, R1 and R10 are expected to be the most preferred path between these two service provider networks. And along this path, there could be a route conditioning facility that must profile the traffic that is traversing or passing through the network for certain reasons, which could be business related. And there are other options which may be security reasons or preference. It all depends on what the business wants actually. And in that case, it means you have to do everything possible to ensure that this particular path is protected from a single point of failure, which means if one of these paths should fail, the traffic flowing from the remote end here towards the campus location must still prefer this path to get there, unless there is a complete failure, which could be a device failure on either of this path or a complete outage on the two paths that you have on this particular network. Then there should be a last resort path which will eliminate a total outage. This is also a part of a business continuity consideration, which says there must be a way out even in the worst scenario, and that is why we have this path as the secondary backup path. However, this is a protected path, but this will then be referred to as the unprotected path. And that is the essence of having to consider the multi-hop option, because here your MP-BGP is formed over these two links between the loopback addresses on the two ASBRs, as you see. And so here I'm just painting a scenario. The essence of using the loopback is to achieve a reliable peering over a link protected reachability path to the peering address, which is the loopback in this case, in the event of an inter-AS link failure between both ASBR, explicitly explained in the previous slide, which is if one link here should fail, the other link is there to sustain that particular path. And EBGP in this case is not impacted because the loopback is learned over a redundant or a protected link. Now, take a scenario for instance. Imagine that you have only a single path and you have this failure. Exactly what will happen is that the traffic will then flow through the secondary backup path. And now, from a design perspective, when the business says we want traffic to always go through a particular path that has facilities to condition their traffic or to provide more security validation or verification on whatever traffic it is, this in that regard will become a failed design, because a single point of failure on this path has exposed whatever traffic is passing through to an undesired outcome, even though the reachability is still there. But you will agree with me, from business perspective, there are several metrics that are used to calculate failure and the rate of successes as well. And so this design, for instance, even though it has redundancy, has failed that critical requirement. That is why we have to consider a redundant inter-AS path, which is the protection for this particular link that could fail, but it doesn't expose this path to a single point of failure as in the other case. And in this regard, this design then can be said to have met the business requirement because of this particular indication of protection from a single point of failure. Now, design generally are not fixed. They are always driven by business requirement. Some other business requirements may say, this is exactly what we want, while others will say, no, we want to replicate the same idea of this point to the secondary as well. It all depends, but always know that for every link you see, there is always a cost attached to it. And for every cost, the business has the responsibility to decide if they can incur such costs or they would rather look for alternatives in order to solve such kind of business problems. And so the next section will be the configuration section. But before then, I will show you a configuration guide for option B using Multihop method. And remember, the requirement of this design is that remote site must be able to reach the servers at the campus site through a preferred path that is protected. Now, if there should be any failure, which is total, that is, the two physical links here fails, the traffic between remote towards the campus must not be completely out. It must always flow through the secondary backup path. And that is exactly the goal of this particular design. And I will show you what to do and where to make these configurations happen. Background information is as shown for the design already. If you have been following my videos in the previous ones, you would see that this has been consistent, and it's only to make it understandable for you as well. And here are the assumptions. The first assumption is that IGP sessions in each of the service provider networks have been converged. We don't want to waste your time on this. And that is why I have to do some pre-configuration, which includes this particular IGP. The same thing applies to MPLS LDP sessions, which is also converged already, and also the MP-BGP, which is the internal MP-BGP, also done. There are no special configuration existing on any of the routers, and VRFs are also configured already on the PEs. Now, the focus of this design of this particular video is based on the multi-hop, and that is the reason I have to pre-configure the MP-BGP session between R4 and R9. So, the configuration required on the ASBR is as shown. Remember to always disable the automatic route filtering feature on the ASBRs, that is on R1, R4, R9, and R10. In order for these ASBRs to have a single global MP-BGP table, which will take care of all the routes coming from all the VRFs that they may have received for. After which, you have to enable MPLS LDP over the inter-AS link between the ASBRs. Now, on these links here, you have to enable MPLS LDP. This is different from the previous options that we have treated because this case requires this feature to be established in order to extend the MPLS path across this link between the two providers. Now, there are options that you can consider. Because you are going to be establishing the peering, or because you're going to be peering between the loopback, there is need for these routers to be able to reach the loopback directly without using BGP. And that is why you can use the static route in order to achieve this by pointing your static route over the two links. If you want to load balance, for instance, the static route will be of the same administrative distance. But if you want to prefer an active standby kind of scenario where one will always be the primary and the other will remain the backup or the protection, then you can put a discrepancy between or difference between the administrative distances between these two routers. But make sure whatever you do is made to be symmetric, because if you have a symmetric kind of scenario and there is a failure on one path, it will affect the convergence of this particular line. And also, if you are using static route, it is always advisable for you to make it more intelligent than just a static route by using a tracker and IPSLA to watch the status of the other side so that it can take it down completely and make one become the backup indeed. So it has to be an intelligent backup. You don't want to be the one manually shutting down the two sides before there is a failover successfully on this path, and so you have to take note of that. Then you have to redistribute the static route into the local IGP. In this case, the local IGP is the OSPF. So you distribute this static route into OSPF as well as the static route on this router into ISIs. After you must have redistributed static route into ISIs and OSPF respectively, it meets the BGP requirements that says your next stop address must be reachable, and that is the essence of the redistribution. And of course, the extension of the LSP, which is the label switched path, is also dependent on that particular feature, because the next stop address that is found in the BGP table is expected to also be in the label forwarding information base table of MPLS in order to have a very seamless kind of switching based on MPLS labels. Then the next part to do is to ensure that you establish eBGP, but in the multi-protocol BGP domain. And you have to specify your source update to be looped back and also the MP-BGP multi-hop value. In this case, it's just one up after this point, which means when you run a trace route from R10 to R1, you will find two ups, which shows that the loopback from this perspective on this router are two ups away. This point and then the loopback, and the minimum that you could specify for eBGP multi-hop on these two routers will be 2, so that they can easily form adjacency on the MP-BGP. Note, on the local ASBR, there is no need to rewrite the next stop address on the received prefixes from the remote ASBR. What this is saying is that you do not need to specify neighbor whatever IP address of the neighbor and next stop self. You don't need to do that, because already you have established that reachability of the next stop by the redistribution that you will do of static route into the local IGP as specified here in this point. And so once you have all these configurations established on the ASBR, then you can focus on the injection of the remotely launched route into the local VRF, and this is done on the PE. Okay, now note, if the route reflector is not used internally, then you have to configure the MP-BGP between the PE and the ASBR directly. However, in this scenario, and this has actually been a consistent design which I have worked with for this particular series of videos on inter-AS MPLS VPN, I am using the route reflector to make the internal routing more scalable, and of course leverage on the simplified configuration of internal peering, and that is the second point here. So if you are using the route reflector internally, then you have to pair with the route reflector, of course, And also you could disable the ARF, that is the automatic routing filtering, on the route reflector in order to get a full copy of the BGP table of all the protocols that are leveraging on BGP. In other words, the MP-BGP table. And so you can either use the import statement on VRF configuration, or you can rewrite RT, as I've shown you in one of the previous videos as well. So doing this makes it easier for you to inject the remotely LAN route into the local VRF, and that makes it so easy without you bothering to do any form of leak into local VRF on the PE. And of course, you have to do your peering on the PECE link, which could be any of the adopted protocols. So, after all the configurations must have been made on these devices, both the ASBR, the route reflector, and the PE, you can then check your reachability between the remote site and the campus site in order to verify that everything has been properly configured. Now, I will take you through the configuration in the next video. Please check the link to this video in the description section. Thank you.